tangible.
Absolutely.
From the chair you're sitting on to the stars, well, everything seems so fundamentally there. But what if I told you that when you zoom way in, when you really probe the depths, that solid reality kind of dissolves. It becomes something far more abstract and honestly pretty mind-bending.
It really does. The question becomes, what is everything really made of?
Yeah.
At the very bottom.
Exactly. So today on the deep dive, we're plunging right into that fabric of existence to talk about quarks, the universe's ultimate, maybe most elusive building blocks.
Yep.
We've gathered a whole stack of sources you've provided, articles, research papers, our notes, and our mission really is to sift through them. We want to pull out the most surprising facts, the crucial insights about these tiny, tiny particles.
It's a dense topic, no doubt.
Oh, yeah. But we'll guide you through the really fascinating parts.
That's the plan. Our deep dive today is all about taking you, our listener, on a journey. We want you to understand not just what quarks are, but why they represent such a huge triumph, and also one of the biggest ongoing mysteries in modern physics.
A triumph and a mystery. I like that.
We'll unpack their bizarre properties, the whole turbulent story of their discovery, and what they mean for how we understand reality itself.
Okay, let's dive in. To really get quarks, we first need to place them, right? Where do they fit in the big picture?
The standard model. That's the framework.
Right, the standard model of particle physics. And the research is pretty clear. Quarks are considered fundamental.
Meaning no smaller parts inside them, as far as we know. Truly elementary.
The foundational pieces.
And that makes them the absolute bedrock of the visible universe. I mean, these quarks combine to form particles called hadrons.
Hadrons, okay, like protons and neutrons.
Exactly, the most familiar ones, protons and neutrons, which make up the nuclei of all atoms.
So everything we see, stars, planets, us.
It all comes down to just two types of quarks, really. Up quarks and down quarks. That's the basis of all common matter. It's kind of amazing.
Okay, but this is where it starts getting weird, almost paradoxical. The first big conceptual hurdle, color confinement.
Yes, confinement.
Our sources hammer this point home. You can never find a quark by itself, not under normal conditions.
No lone quarks floating around.
Right. They only exist inside these composite particles, hadrons, which are color neutral, or I guess in this really exotic state, a Quark-gluon plasma.
Which we'll get to. But yeah, that inability to isolate them, the fact that these supposedly fundamental things are unobservable on their own, that was a huge hurdle initially.
I bet. It must have caused so much skepticism. It kind of defies intuition.
Absolutely central, that paradox. But there's more that makes them unique. Two other big things.
Okay.
First, they're the only elementary particles we know that feel all four fundamental forces.
All four. So strong, weak, electromagnetic, and gravity.
Yep. The strong interaction, weak interaction, electromagnetism, and gravitation. Think about electrons. They're leptons. They don't feel the strong force at all.
Huh. So quarks are connected to everything.
In a way, yeah. They have mass, electric charge, flavor, this color charge. They're the most, let's say, social particles.
Okay, social particles. And the second thing?
The second thing was, well, revolutionary. And definitely controversial at first, fractional electric charge.
Ah, right. Not whole numbers.
Exactly. Every other elementary particle has a charge like +1, -1, or 0 in fundamental units. Quarks, they come in +23 or -13.
Plus 2/3 or -1/3. That is radical. No wonder people were skeptical.
Deeply skeptical. It just didn't fit the pattern.
Okay, so we have these confined, universally interacting, fractionally charged particles. But wait, it gets even more complicated, doesn't it? There isn't just one type.
Nope. There are six distinct flavors.
6 flavors.
Up, down.
Charm, strange, top and bottom.
Up, down, charm, strange, top, bottom. And they're organized, right, into generations. 3 generations, yeah. Each generation has a pair of quarks and a corresponding lepton, like the electron in the first generation.
Why 3 generations? Does anyone know?
That's one of the biggest unanswered questions. A deep mystery. It strongly hints there's physics beyond what we currently understand.
Wow. Okay, so let's break down the generations. First generation.
That's the up, U, and down,
Yeah.
the quarks. They're the lightest, the most stable. And crucially, they form protons that's 2 ups and a down.
2 ups, 1 down. Got it.
Neutrons, 1 up, 2 downs.
1 up, 2 downs. Okay, so that's the basis of all stable matter, the everyday stuff.
Precisely. Then the second generation brings in charm, C, and strange,
Like
trade.
and strange.
And the third generation gives us top T and bottom B.
Top and bottom. I love the names, by the way. The sources mention where they came from.
They are pretty whimsical, aren't they?
Strange, because particles with it lasted strangely long.
And charm, because finding it made the theory work like a charm.
And my favorite, top and bottom, used to be truth and beauty.
That's right. Gives you a sense of the human element in all this abstract physics.
It does. But what's really striking is the difference in their masses, right? The hierarchy.
Oh, it's dramatic. The mass hierarchy. Up and down are incredibly light, almost negligible mass.
Practically massless.
But then you jump to the top quark. It's staggeringly heavy. It's the most massive elementary particle ever found.
How heavy are we talking?
Comparable in mass to an entire atom of gold.
An elementary particle as heavy as a gold atom. That's hard to wrap my head around.
It is. And this huge mass difference is directly linked to stability. The heavier quarks charm, strange, top-bottom, they're highly unstable.
So they decay.
Rapidly. They decay into the lighter first-generation quarks. That's why we don't find them lying around in ordinary matter.
But they exist somewhere.
They're produced fleetingly in high-energy collisions, like in particle accelerators. And we think they were abundant in the very early universe, just after the Big Bang, the so-called quark epoch.
Okay. And quick clarification, antiquarks, they exist too.
They do. For every quark, there's an antiquark. Same mass, same spin, same lifetime.
But opposite charge-like properties, like electric charge.
Exactly. Opposite electric charge, opposite color charge, and so on.
Yeah.
It fits the symmetry we often see.
But does this antimatter aspect make things even more complex?
It feeds right into one of the biggest mysteries, actually, what we call the flavor problem.
The flavor problem, okay.
So the standard model lists these three generations, right? It catalogs them perfectly. But it offers zero explanation for why there are three, why these heavier, unstable copies of the first generation exist at all.
If all stable matter is just ups and downs, why the others?
Exactly. The model just puts them in because we see them in experiments. It doesn't explain why.
So the standard model is successful, but incomplete.
That's what it strongly suggests.
Yeah.
It's an incredibly effective theory, but this pattern, this flavor problem, is a massive clue pointing towards deeper physics we haven't grasped yet.
Okay, so these fundamental quarks are bound together incredibly tightly, you said, by the strong interaction.
The strong interaction, yes. The most powerful of the fundamental forces. And the theory that describes it is called Quantum Chromodynamics, QCD.
QCD, got it.
And QCD is where things get really, really weird and interesting.
More weirdness, bring it on.
It starts with color, this concept of color charge.
Not actual colors, right?
No, nothing to do with light we see. It was proposed to solve a theoretical problem. There are particles, like one called the delta ++, made of three identical up quarks.
Okay.
But a fundamental rule of quantum mechanics, the Pauli exclusion principle, says identical fermions like quarks can't be in the exact same state.
So how could three identical ups exist together?
They needed a new property to distinguish them. So physicists proposed color, red, green, and blue. Each quark has a color. It's the charge of the strong force.
Red, green, blue.
Okay.
And what carries this force?
Gluons. They're the particles that mediate the strong force. They literally glue quarks together.
Gluons, like photons carry the electromagnetic force.
Similar idea, yes. They're massless gauge bosons. But here's the crucial difference, the thing that makes QCD unique.
What's that?
Unlike photons, which are electrically neutral, gluons themselves carry color charge.
Wait, the force carriers also have the charge they're carrying?
Exactly. Each gluon carries a combination of a color and an anticolor, like red anti-blue. There are 8 types. This self-interaction, gluons interacting with other gluons, is fundamental to how the strong force behaves. It's unlike anything else.
Okay, that is different. So this self-interaction leads to confinement.
It leads to both confinement and something else equally strange. Asymptotic freedom.
Asymptotic freedom. Right, you mentioned that briefly. It sounds like a contradiction. Confined but free.
It does. Asymptotic freedom means that strong force gets weaker as quarks get closer together, or as the energy of their interaction goes up.
Weaker when closer. That's the opposite of gravity or electromagnetism.
Totally counterintuitive. At extremely high energies, quarks inside a proton, for instance, act almost like they're free particles barely interacting.
And that was a big deal, discovering that.
Huge. It was discovered in 1973 by Gross, Wilczek, and Pulitzer. Earned them the Nobel Prize in 2004. It showed QCD was on the right track.
So they act free when they're close or hit hard.
Exactly. But then, try to pull two quarks apart. That's the other side of the QCD coin. color confinement.
Okay, what happens then?
The force doesn't weaken with distance. It stays constant, incredibly strong.
Constant force no matter how far apart. How does that work?
Imagine you're stretching a rubber band. The more you stretch it, the more energy is stored. With quarks, it's like an unbreakable band. A flux tube or string of energy forms between them.
A string of energy.
Yeah, and the energy in this tube grows linearly with distance. Pull them further apart, more energy gets stored.
So what happens? Does the string just keep stretching forever?
Eventually, the energy stored in the string becomes enormous. So large, in fact, that it becomes energetically cheaper for the vacuum itself to spontaneously create a new quark-antiquark pair.
Pair production.
Yeah.
Out of the vacuum.
Yep. This new pair pops into existence, the original string snaps, and you end up with two separate hadrons instead of one isolated quark.
Wow, so the force is so strong it creates new matter rather than letting a quark go free.
That's the essence of confinement. It's an ingenious mechanism.
And this ensures only color-neutral things exist freely.
Precisely. You either get baryons, 3 quarks, one red, one green, one blue, which combine to make white or neutral.
Like protons and neutrons.
Right. Or you get mesons, a quark and an antiquark. A color and its anticolor also combine to make white.
Like pions and kaons, the sources mentioned.
Exactly. Those are the only combinations allowed out in the open.
Okay, this is profoundly weird, but it connects to something really fundamental, doesn't it? Mass.
Yes. This is one of the most mind-blowing consequences of QCD and confinement. Where does the mass of ordinary matter come from?
Well, I'd assume from the mass of the quarks themselves, the up and down quarks.
You'd think so. But their intrinsic mass, what we call the current quark mass, is tiny. It accounts for only about 1% of the mass of a proton or a neutron.
1%. Where does the other 99% come from?
It's an emergent property. It comes mostly from the energy of the system, the kinetic energy of the quarks whizzing around inside the hadron, and even more significantly, the energy stored in that powerful gluon field binding them together.
So mass isn't just the stuff, it's the energy holding the stuff together. EMP-IME in action.
Exactly that. Einstein's famous equation, right there at the heart of matter. The vast majority of the mass of the visible universe is generated by the strong forces binding energy.
That's incredible. 99%. It just changes how you think about what mass even is.
It really does. It's one of the deepest insights from QCD.
So how did we even get here? Confirming these bizarre confined particles couldn't have been easy.
Oh, it was a saga. A real textbook example of the scientific method theory. Prediction, confusion, experiment, surprise, refinement, spanning decades.
It started with chaos, right? The particle zoo.
Exactly. The 1950s and early 60s, particle accelerators were finding new particles left and right, dozens of them, all short-lived mostly.
A zoo. Too many to all be fundamental.
That was the feeling. There had to be some underlying order, some simpler building blocks.
And the first step towards order was?
The eightfold way, developed independently by Murray Gell-Mann and Yuval Ne'eman around 1961.
Like a periodic table for these hadrons.
Sort of. It grouped them into families based on their properties, like charge and strangeness. And remarkably, it predicted the existence of new particles that were later found, like the omega minus.
Okay, so that organized the zoo, but it didn't say what they were made of.
Not yet. That came in 1964. Gell-Mann, and working completely independently, George Zweig, proposed that hadrons were built for more fundamental things.
This is where quarks come in.
This is it. Gell-Mann called his entities quarks, famously taking the name from a line in James Joyce's Finnegan's Wake, 3 quarks for muster mark.
3 quarks, fitting for baryons, and Zweig.
Zweig called his aces. But the core idea was similar. Hadrons weren't fundamental.
But these ideas were radical, right? Fractional charges, confinement.
Extremely radical. They were met with widespread skepticism, even dismissal. The sources say Gell-Mann himself was quite cautious, even doubtful at times, about whether quarks were physically real or just a useful mathematical trick.
Shows how counterintuitive it was. So what was the turning point? What provided actual evidence?
The experiments. Specifically, the deep inelastic scattering disk experiments at the Stanford Linear Accelerator Center, SLAC, in the late 1960s.
Deep inelastic scattering, what do they do?
They fired high-energy electrons at protons and neutrons. Think of it like using tiny probes to see inside.
And what did they see? Not just a fuzzy ball.
Not at all. Earlier, lower-energy experiments had suggested the proton was sort of soft and diffuse, but disks showed electrons bouncing sharply off hard, point-like objects inside the proton.
Quite like things. Inside the proton, like Rutherford finding the nucleus.
Very much analogous to Rutherford's gold foil experiment, yes. It was a seeing inside the proton moment.
And these point-like things, Were they quarks?
Well, the theorist Richard Feynman initially just called them generic internal constituents, partons.
Partons.
But then came the crucial measurements, also at ESLAC and at CERN in Europe between 68 and 73. They measured the properties of these partons. They found these partons had spin 12, like quarks were predicted to have, and the clincher. They had the exact fractional electric charges, plus 23 and negative 13, that Gell-Mann had proposed for quarks.
That had to be it. Compelling physical evidence.
It was the first truly compelling evidence, yes. It shifted quarks from being a maybe mathematical idea to something physically real inside protons and neutrons.
And QCD, the theory of the strong force, explained the lingering paradoxes.
Perfectly. Asymptotic freedom explained why the partons looked free when hit hard by the electrons in the DIS experiments.
Because the force gets weak at high energy or close distance?
Right. And color confinement explained why, despite being real, they were permanently trapped inside the hadrons and couldn't be knocked out individually.
Wow. It all clicked together.
Beautifully. And the final nail in the coffin for any remaining skepticism came in 1974.
What happened then?
The November Revolution. Two experimental groups, one at Brookhaven Lab and one at SLAC, simultaneously discovered a new particle, the Jess Mason.
Jeffsay. Okay. Why was it so important?
Its properties, particularly its surprisingly long lifetime, could only be explained if it was made of the new fourth type of quark, the charm quark bound with its antiquark.
The charm quark, the one that made the theory work like a charm.
That's the one. Its discovery cemented the quark model. Quarks were no longer speculative. They were an accepted essential part of physics.
So with quarks and QCD established, what's the focus now? Where does the research go?
A lot of it involves pushing the theory to its limits. Stress testing it, you could say, in extreme conditions. Exploring realms where QCD predicts really exotic behavior.
Like the early universe.
Exactly. One major area is the study of quark-gluon plasma, or QGP.
The quark soup.
Right. QCD predicts that if you get matter incredibly hot, trillions of degrees Kelvin, and incredibly dense, protons and neutrons should essentially melt.
Melt?
Yeah, dissolve into their constituent quarks and gluons, which are then temporarily deconfined, free to roam around in this plasma state.
And these are the conditions right after the Big Bang?
For the first few microseconds, yes.
Mm-hmm.
The entire universe is thought to have been a QGP.
Can we recreate that?
We try. At big collider facilities like RHIC at Brookhaven and the LHC at CERN, scientists smash heavy ions like gold or lead nuclei together at almost the speed of light.
Creating tiny, fleeting fireballs of QGP.
That's the idea. Tiny droplets lasting for an unimaginably short time. Maybe 10 to the minus 22 seconds.
Yeah.
It's long enough to study indirectly.
How do you study something that vanishes so quickly?
By looking at the particles that fly out as it cools and freezes back into normal hadrons, there are specific signatures we look for.
Like what?
Two key ones are jet quenching.
Jet quench.
Yeah. Sometimes in these collisions, a quark or gluon gets knocked out with very high energy, creating a jet of particles. If that jet has to travel through the dense QGP, it loses a lot of energy, it gets quenched. Yeah. Seeing that energy loss tells us the plasma was there.
Okay. And the other signature?
Heavy quarkonia suppression. Remember the Jemison? Charm quark and antiquark.
Yeah.
Well, heavy quark pairs like that, called quarkonia, tend to get screened or melted apart within the hot QGP. Observing fewer of them coming out than expected acts like a thermometer for the plasma.
Fascinating. So what have we learned about this quark soup? Is it like a gas?
That's what people initially thought may be an ideal gas of nearly free quarks and gluons because of asymptotic freedom. But the experiment showed something surprising. The QGP behaves much more like a liquid. In fact, a nearly perfect liquid with extremely low viscosity, meaning it flows almost without resistance.
A perfect liquid, not a gas.
Nope. It turns out to be one of the most strongly interacting fluids known, which tells us a lot about the nature of the strong force even at these extreme temperatures.
Wow. Okay, so QGP is one frontier. What else?
Another really exciting area is exotic hadrons.
Exotic, meaning not just the standard 3-quark baryons or quark-antiquark mesons.
Exactly. For decades, those are the only types we knew. But QCD itself doesn't actually forbid more complex arrangements, as long as they are overall color neutral.
So like 4 quarks, or 5.
Precisely. And starting around 2003, especially with results from the LHCb experiment at CERN, physicists have discovered a whole new zoo of particles that don't fit the old mold.
Good jazz.
Tetraquarks. Particles made of 4 valence quarks. For example, 2 quarks and 2 antiquarks, like the Z4430 particle they found.
4 quarks bound together, and 5.
Pentaquarks, made of 5 valence quarks, typically 4 quarks and 1 antiquark. LHCb announced the discovery of pentaquark states, like the P4450 plus TUS back in 2015.
Tetraquarks and pentaquarks. So the hadron family is bigger than we thought.
Much bigger and more complex. It's opened up a whole new field of spectroscopy.
Is it clear how they're structured inside? Are they single particles or more like molecules?
That's the big debate. Are they tightly bound single exotic states, or are they more like loosely bound hadronic molecules, maybe a meson and a baryon sticking together briefly?
Different models predict different things.
Right. And studying these exotic states, figuring out their internal structure, is a fantastic way to test our understanding of QCD in a completely new regime beyond just protons and neutrons.
So even with all this success, QCD, quark model, QGP, exotics, there are still big holes in the picture.
Oh, absolutely. The standard model, including quarks and QCD, is phenomenally successful at describing how things work, but it's often silent on the why.
It points towards physics beyond the standard model.
That's the term, yes. The limitations and unanswered questions within the standard model itself are seen as powerful clues pointing towards a deeper, more fundamental theory.
What are the biggest quark-related puzzles still bugging physicists?
Well, we already touched on some. The generation problem is huge. Why 3 generations of quarks and leptons? Why this triplication of matter? The standard model just accepts it as an input.
No explanation.
None. Then there's the mass hierarchy problem. Why do the quarks have the masses they do? They span this enormous range, 5 orders of magnitude, from the light-up quark to the incredibly heavy top quark.
And the model doesn't predict these masses?
Not at all. We have to measure them experimentally and plug the values into the equations. There's no understanding of why these specific masses arise or why the hierarchy is so vast.
Okay, what else?
More theoretical one. We still lack a rigorous, purely mathematical, analytical proof of confinement.
Even though we see it and computer simulations support it.
Exactly. We know QCD is confining based on experiments and strong computational evidence, lattice QCD, but a formal proof starting just from the equations has remained elusive. A major challenge in mathematical physics.
Like knowing the bridge holds up but not having the final mathematical blueprint.
A good analogy. And finally, there's the strong CP problem.
Strong CP. Something to do with symmetry.
Yes, charge parity symmetry. The equations of QCD naturally allow a term that should cause a noticeable violation of this symmetry in strong interactions. But experiments show that if this violation exists, it's incredibly, unexpectedly tiny, close to zero.
Why is it so small?
Nobody knows. It seems unnaturally fine-tuned. Explaining this suppression is another major puzzle.
So all these puzzles, they lead back to a really fundamental question, don't they?
The ultimate reductionist question. Are quarks truly elementary?
Or is there something inside them?
Exactly. Physics has progressed by finding layers. Atoms, nuclei electrons, protons, neutrons, quarks. Does it stop there, or is there another layer down?
Didn't some people propose something smaller? Preons?
Yes, the preon hypothesis emerged in the 1970s. The idea was that maybe quarks and leptons aren't fundamental, but are themselves composed of even smaller point-like particles, preons.
Was that an attempt to explain things like the 3 generations?
It was one motivation, yes. Perhaps the different generations were just different arrangements or excited states of these underlying preons. It aimed to simplify the particle zoo further.
So how do we test that? How do we look for preons or quark substructure?
By smashing particles together at extremely high energies, like at the LHC. If quarks have internal structure, hitting them hard enough should reveal it.
Ow!
One signature people look for is excited quarks, Q. If a quark is composite, you might be able to briefly knock its constituents into a higher energy state, creating a heavier, excited version of the quark, which would then decay.
Like exciting an electron in an atom.
Similar principle. You'd look for specific decay patterns or resonances at very high energies.
Have they found anything? Any sign of excited quarks or preons?
Here's the kicker. No evidence whatsoever.
None.
None. Years of searching at the highest energies humans can achieve, and quarks still look perfectly point-like.
So that puts limits on their size.
Extremely stringent limits. If quarks do have substructure, it must be smaller than about 10 to the minus 19 meters. That's incredibly tiny.
10 to the minus 19. Hard to even imagine. If a proton was the size of the Earth?
A quark, if composite, would have to be smaller than a grain of sand on that Earth.
Wow.
So this null result, the failure to find preons or substructure, is actually a profound result in itself.
Oh, so?
It tells us either that quarks truly are fundamental, the end of the line for what things are made of as we currently probe it,
Yeah.
or or that the nature of compositeness, if it exists at this scale, must be radically different from anything we've conceived of before. Maybe preons are bound by some new, incredibly strong force, or maybe the concept of parts within parts breaks down entirely at this level.
So the mystery deepens even in the absence of discovery.
In many ways, yes.
Okay, as we wrap up this deep dive then, it's been quite a journey. Quarks started as this almost whimsical mathematical idea to tame the particle zoo.
A way to bring order.
And now they're a confirmed cornerstone of reality, but still so paradoxical fundamental, yet utterly confined. You can't grab one.
Never alone. And the theory describing them, QCD, it hasn't just explained quarks, it's radically changed how we understand force itself.
Especially with that revelation about mass.
That staggering fact. 99% of the mass of the visible universe isn't from the intrinsic mass of quarks, but it's an emergent property of the strong force's binding energy. E-NDSCS, it's the energy of the glue.
It's mostly the glue, not the bricks. Mind-bending.
And the exploration is definitely not over. It's accelerating, really.
Recreating the early universe in Quark-gluon plasma.
Discovering exotic tetraquarks and pentaquarks that challenge our models.
The field is constantly throwing surprises at us.
But those deep mysteries remain. They hang over everything.
Why 3 generations? Why the huge mass differences?
And are quarks truly the bottom floor? Or is there something deeper still?
These aren't just academic questions, are they? They define the absolute cutting edge of fundamental physics.
They're the driving force behind the next generation of experiments, the next theoretical leaps. They're pushing us to understand the universe at its most fundamental level.
So the quark, it's more than just another particle. It's like a gateway, isn't it? A gateway to understanding the deepest rules of the cosmos.
Beautifully put. It ensures quarks will remain right at the epicenter of physics for a long time to come.
Which leaves you wondering, what other hidden depths, what other organizing principles might still be lurking within the very fabric of existence, just waiting for us to find the right questions to ask?